And the school that I belong is the School of Engineering. We do have a bioengineering, but I belong to chemical engineering as a bioengineer. We have a very unique program for the undergraduates. In order for them to have the degree, they have to complete 3 co-ops. So every other semester they go to industry, and then they get experience and come back and then finish. So we don't have a summer off, because in order for them to graduate within 4 years, we have to have a summer. So that's unique one. And if you have another year right after the BS with these 3 co-ops, then you can also get something called Master of Engineering. But that is only for the student who went through all these co-ops. Department Chemical Engineering. I am kind of odd in the department because I'm probably one of 2 faculty members who does bioengineering, because I was supposed to belong to bioengineering and it just didn't happen. And most of the research right now is focused on renewable energy, so they use some nanoparticles also. That's about it, and I think probably now you are tuned to the main topic. So one of the things that when you think about nano, you know what? I have seen so many cathedrals. Do you know any kind of relationship with the nanotechnology and then cathedral?
So glasses and something.
Yeah. What is the color of golden nanoparticle? What do you think it is? Gold color? What is it? It's red. The one that you see in the stained glass. So what it is, basically, the size is smaller than your light wavelength. So it's not representing bulk color. So if you look at the size, this is bio size of one of the larger enzymes. That's about 10 nanometers. That is the particle size that I'm using. So good thing about it is I think I skipped that because I thought you might already have the nanoparticle. So when you use nanoparticle, it's good to fix the problem more fundamental level, because it's a smaller. It goes to either molecule or the cell level. So it is good, but it also is good because it's circulated in the bloodstream longer times. You don't have to inject so many times. And the cell uptake rate is usually better with the size. And then it has a lot of other properties, but it's one of the good properties. So when you use the nanoparticles, you're going to have to check short-term and long-term toxicity. Short-term is usually easy because you can just do the cell toxicity study, but long-term is usually accumulation in the excretory organs, like a kidney, liver. So that needs to be, and it takes really long time. So I think we are at the stage that we're still studying on that. We are not done that yet. It's a good because you can have a multifunctional, because surface area is rather large, you can put many other functions. And you can, by putting all this specific, the targeting molecule, you can make it highly specific. You can have a high efficacy because it stays in a longer, in the bloodstream longer. And then minimally invasive administration is a good thing, but it depends upon how you use. I mean, minimally, it's probably you inject something and then, or sometimes you can put in certain places. The thing that you really have to worry about is after you use, if you can actually make this go away. So the one that they're using a lot right now, actually for the treatment, is polymer particles, because you can make it large, but once it is used, it disintegrates and you can just go out. And that's actually right now used for cancer treatment. The person who is really well known in this field is somebody called Mark Davis, and he's in Caltech right now, but he's I think he started the nanotechnology because his wife died by cancer, so he started. So he's a very good one, and if you want to study about polymer particle, he's a good person. And liposome is also used clinically. Dendrimer is also used. I don't know whether it's actually clinically used or not, but I think there's a clinical studies. Gold nanoparticles are tested from, I think, less than 3 years, but it is clinically tested. Gold nanoshell has been clinically tested for hypothermia, and iron oxide particle. It was used usually mainly for MRI contrast agent. Now it is used for cancer treatment. Quantum dots are used extensively for experiment studies, but you cannot use it for human because it's toxic. So what am I doing with the molecular imaging? Molecular imaging is a little bit different from imaging that you go to the hospital and they do MRI, except I think PET, they are definitely using contrast agents. Molecular imaging is something that is targeted. So you are making some portion that you like to observe more with more contrast. So I do not know your specialties, but if you look at this one, and you see this kind of thing in nature and science a lot, the cells do not look like this. It's all by the fluorophore. So, I mean, you can study a lot of these things with the cells. If you have a really high specificity, it goes only the place that you want it to go, and then with a high sensitivity, any sensing is that's two, specificity and then sensitivity. That's giving you earlier disease diagnosis, and then also you can see things, you can study things much more specifically, whether this is causing this, this is causing that. Okay, so this is one of the NIR fluorophore that is targeting tumor here. So targeted imaging is molecular imaging. In my case, I am using fluorophore. I do near-infrared imaging. So the problem about near-infrared imaging is, especially for the breast cancer detection, usually what they do is when the cancer grows, you have this large accumulation of blood because the angiogenesis is holding a lot of blood. And they want to see whether this has more absorption, and you know, whether there's a cancer in the bed. That's not really specific. So if you want to use fluorophore and then make this one more with more contrast, that could be minimally invasive detection. So fluorophore is you get the light at one wavelength, so the electrons of these molecules get all excited, and then it has to go down. When it goes down, you emit another wavelength. That's the fluorophore. So if you have this one to be as high as you can get, that's the good thing. So these phenomena is called, it's caused by electron states. So if you put some entity which is changing the electron state of the fluorophore, that's the thing that you can actually manipulate the fluorophore light intensity. So one of the particles, nanoparticles, that does well is gold nanoparticle. And for the human being or for the animal study, you can only use particle which is not toxic. So you do not have a lot of choices. So you do gold nanoparticle. So you have this light is going into the particle, and the electrons around the nanoparticle get all excited, and it's forming an electromagnetic field. And that's called, we usually call it Plasmon field. And this is also used for, strange enough, this kind of thing is also used for renewable energy in solar cell. And it's not like this one, but basically changing the energy form. So we use this concept for bio, but it's also used for energy, renewable energy. So what you want to do is you want to put this one near to somewhere fluorophore, manipulating the electron state. So particles wise, you don't have a choice in the bio, so we use gold nanoparticle. particle size is important because when the particle size is large, the plasma field strength is usually stronger. Wavelength can also affect, but when you have a fluorophore at a designated excitation when emission, you don't have a choice, so you can probably, you cannot really change the wavelength. Distance is also important. The plasma, the field strength exponentially decays from the surface. So I think you're an engineer, so I will give you one equation, but what it is basically, when you have this photon energy coming to the gold particle, it doesn't change the quantum efficiency. It'll go to excitation and emission cycle faster, so per time you're getting more light coming on. But then again, it also changed the quantum yield. It's not actually the quantum yield that the traditional concept of quantum yield. It's basically absorb the apparent quantum yield. So when the gold particle absorbs all the light from here, emitted, you make this one very strong, but it itself is absorbing. You don't have light coming on. So the wavelength is important. The particle, I mean the particle absorption, the wavelength should be far away from usually the wavelength that you want to use. So if you look at in a qualitative sense, this is the fluorophore intensity when you don't have any gold particle. If you go near to the gold particle, this is a fluorophore. At certain point, certain distance, it shines really well, and then at the surface of the gold particle, it quenches 100%. So, and we have all this theory, but I'm not going to go through because we don't have enough time. But if you use the quenching thing, you can actually do the negative quenching. Whenever this get together, I lose photons, which means the intensity goes up. You can use that, or you can enhance the fluorescence. You can use this part, so you have a better sensitivity. So I don't know if you guys do any kind of molecular sensing or not, but this is the fluorophore that people usually use. In biosystem, they use all of these. If you look at the order of this one, it's a wavelength shorter to longer. I'm using the one here because that's for it. We can use that for human being. So with the 10 nanometer gold particle, all these fluorophores, distance from 0 to 10 nanometers, all of them are quenched. If you use larger particles, initially it's quenched. At a certain point, this becomes enhanced. If you use even larger one, you can enhance as much as this one, but you can still have a quenching here. So in my case, we're using something called SciPay. That's clinically it is used as cardiogram. They use this one as a not fluorophore but absorber. When they have a heart blockage, they inject this one and see where is the blockage. They also use it for retina examination. So it is clinically used, but that's cardiogram or indocyanine green does not have a side chain to bind some other molecules. So we have to change the molecule a little bit. So we have the COOH, so that we know amino acid and NH2, or those things can be bind. So we are using this one. When we simulate the excitation, I mean the emission light affected by gold particle, you're changing the size of the gold particle here and the distance here. Very near to the surface, you have a 100% quench. At certain point of time, if you use large particle, you can get as much as like almost 10 times higher intensity. So in our case, what we do is, I was talking about this one and this one. We plan to use both of them to have even specificity. How it works? Okay, this gold particle is combined with the fluorophore here with one short linker and one long linker. The short linker has a substrate which is going to be degraded by enzymes secreted by cancer. So, and this is a cancer targeting molecule. So what happens is, if it goes to, initially it doesn't emit a lot of light because this short linker is putting this thing very close to the surface of the gold particle. So it doesn't shine a lot. When it is injected to the human body, it'll go to the cancer site, which is going to be done by the targeting molecule. And then the cancers usually secrete a lot of enzyme to invade. So now we are close to this enzyme secretion. So it is binding to the cancer cell now, and this yellow round thing is going to go here, and it's going to cut the short linker. And then now the light is enhanced much more. I don't know whether you guys know about molecular beacon. Have you heard about molecular beacon? They use something like this with the quencher molecule. They don't use particle, but they use only for DNA segment. Here, we don't have that restriction. So we did this study with a model system, which is urokinase type plasminogen activator. That's the enzyme secreted by one type of breast cancer. And then this short linker has GGR peptide sequence. And we have this linker with the side to the gold particle has the hydrophobic, the other side has to be hydrophilic. So it's a combination of hydrogen, carbon, and the PG. So this is side A, and this is the linker, the short linker that we're going to use. So normally the fluorescence is at 1. If you conjugated the gold particle with the short linker, it becomes like only 5% emission. It's about 3.7 nanometers, and then when you bind this one to 8 nanometer particle, you have about 6%. When you use a larger particle, instead of quenching, it's enhanced. So you cannot use that particle. Enhancing is a good thing, but we're having longer space. So we decided not to use this one. We're using this one. The long one, we need to somehow change the length. We're changing hydrocarbon length here, and there's a pH length. This expected length is by the molecular simulations. It's not really accurate because it's they do simulate in the vacuum. So when it goes, but we have to start somewhere. So we are doing this one. For the long linker, again, when you bind this the fluorophore through this long linker, when it is short, we're having quenching here. When we have this kind of combination, this one and this one, we're having enhancements. We are testing this one with the previous one, short linker together. So initially we thought we have this short linker, now it's working, and we have a long linker working. So we can put it together like that. We tried and it doesn't work that way because this doesn't necessarily go to here. It goes to the particle next to it. So we keep having this precipitation. Nothing is coming out. So we didn't know what to do. So we thought about it, and then these are by the grants. So you need to have some kind of progress, and we're having a lot of problems. So what we thought was, well, let's have only one binding site to the gold, one binding site to the fluorophore. So we made a circle here. So this is a long linker. This is a short linker. And you have one binding site only for the site A, fluorophore, one binding site for the gold particle. And the mechanism of binding here has to be different from this one. So we did that. So after we finished this one, we're having initially from here to this much. Once you add the enzyme, it went up to here. So now this will work only when the cancer secretes UPA. We are still doing the targeted molecule side. Now we have to put another molecule side, so it's going to take some time. But this is the current status of our study. So changing the topic a little bit, we also use some of the gold nanospheres, which, the inside is empty here. The good thing about this one, it absorbs the near-infrared light very strong. So when you apply this one, certain place when the cancer is present, then you can actually apply the NIR and you can hit out cancer. And I have a friend who is making this one. So in our case, they do also hyperthermia, NIR absorption, all those things, but gold particles can be also natural X-ray contrast agents. If you want to do multiple modality imaging, that's a good thing. In our case, we just wanted to try with the conditional emission. So initially, what we did was, you have this thing, and then once this is disconnected, then you have fluorescence coming out. So this is one of the study results. Initially, the fluorescence was here. When you put the UPA here, it went up. So this is another thing probably you can use with a combination of, once you find the cancer, then you can probably apply NIR to treat the cancer, hypothermia. Optical immunosensing. This is another thing that we do, and then we work with the MEMS people to make this one. This is an optical fiber. So immobilized monoclonal and antibody for whatever you want to detect. So in our case, we are doing cardiac biomarker. When somebody has some kind of symptom of cardiac arrest, then the proteins are leached from the heart muscle, so you have this leakage. So we are detecting those things, but it has to be highly sensitive to do early diagnosis. So initially you apply the sample, and then these are the samples, and you wash this one after binding, and you do have a second antibody with a fluorophore, and apply the excitation light. You have an emission light coming in, and then emission light is actually correlate with the amount of the analyte. So this empty diamond is the one without gold particle. The one here is with the gold particle. So you have this enhancement of the high sensitivity. We're actually measuring this one in one sensor altogether. So the final output is, this is the 4 sensor in one MEMS device. And you can see this is a quarter of the American coin. And the sensor side is 1.5 centimeter. You only need about 200 microliter. You can measure all this one within 15 minutes. So we are making also sensor, optical sensor, real-time, almost near real-time sensing. The next one is, I'm going to just show you very briefly the contrast, CT contrast by the gold particle. You can see the concentration of gold particle increases. You have this sensitivity of CT. And we also do hypothermia. If you have a nanomagnetic particle which is inserted to cancer site, you can hit the particle, and then that is depending upon the size of the nanoparticle and amount of the particle. So what happens is this polarity change, but at the same time, the physically it's actually rotating. So if the particle gets really big, it doesn't rotate as much, so it doesn't generate heat as much. So this is also depending upon the probe configuration. So if you want to put the animal inside, that's okay. It's very, very difficult to put human being here because it's really small and confined. So we are focusing on breast cancer. We are changing the configuration of the probe. If you have a pancake shape, then you only have a surface intensity high. I mean, this is a magnetic field, by the way. So if you have two of them, then you can actually add up So depending upon how deep the tumor is, I mean, I am assuming this one to be the breast tissue. So when there is a tumor here, this is not going to be really effective. So usually detection or adding the heat to this type of cancer in the middle is usually difficult. So I am going to skip this one because it's just, we have another topic. So basically, I'm showing various nanoparticles doing sensing and also treatment. So what if you put everything together? And this is not just, I'm not the only one who's doing it, everybody's going for it. So what we want to do was iron oxide inside, magnetic particle, and then coating the gold, and we have a optical fluorophore that is going to give us optical sensing. This particular one inside is going to give us the MRI contrast. This is going to give CT contrast. This must be drug or targeting molecule. So why do you need a multiple imaging contrast agent? It's because optical or PET is very sensitive, but it doesn't give you very good resolution. There's something, but you don't know how big it is, so you need to have another one like an MRI or CT. So if you have a multiple imaging modality, you have a better accurate diagnosis and as well as early. So this probably is the one that we're gonna go for. So for human, again, the non-toxic material has to be used. And also the surface treatment is very important. I'm skipping a lot of information, but it's probably for several papers all combined together. It shouldn't be precipitating. It shouldn't be causing the blood clot. It shouldn't be it should be staying in the blood for a long time, so you don't have to inject a lot. It shouldn't be accumulated in the excretory organ. The size has to be properly chosen, and the surface treatment has to be well done. So usually degradable nanoparticle is good, but not everything nanoparticles can be used, as a degradable. So as you can see, all these things, in order for us to make all these things working, it has to be engineers, it has to be physicists, it has to be also biologists, it has to be somebody from clinical side. So it has to be multidisciplinary to make the nanoparticle work, properly work. So that's the first topic. I'm gonna wake you up for the second talk, because the reason that I'm doing it, this is not only just letting you know what this is about, but I would like you to comment on this a lot, because there are things that I don't know what to do about because it's so difficult. So any kind of comment will be fine, especially if any MEMS people can help me on this. I talked to MEMS people. They were not able to help, but they may not be as good as you are. So this Primo vascular system, it's really new. I think you heard about it for the first time. I heard about this for the first time in 2007 during winter time. So here it looks really good, but this size of this one is only the size of your hair. This is called the Primo vascular system. It's a one subtype of Primo vascular system. It's a Primo vessel, and this is a Primo node. We call Primo nodes. This is a PNPV. This was found by a person in North Korea during 1960s. And North Korea, though it was a very, very, very fantastic research achievement, is that they translate one of the 5 reports in, I think, 3 different languages or 4 different languages, and they distribute this one to entire world. So if you go to your health science library, you may be able to find it. At that time, it's not called the Primo vascular system. It was called Bonghan system by the person first discoverer, and suddenly he disappeared. So everyone wanted to repeat, but in this report, he did not. He skipped the technique that how he was able to observe. I think it's, in my opinion, I think it's intentionally he did, I think. So you need to start from the beginning. So there was another person in 2002, another Korean, but from South. He started again, and they started to find it. The problem is he just could not repeat it all the time. So the reason it's very, very difficult to find is because it's small and it's semi-transparent. So the size of this one is usually less than 1 millimeter, and this is usually 20 to 50 micrometers. And inside of this one, you also have a sub vessels, which means you have even smaller vessels inside. It is known that the cells inside, it's storing some cells, that the cells are expressing stem cell biomarker. That's why it is kind of very interesting. So you need to have somebody who does microsurgery. Even then, you need to be shown how to do it first time, because it's so difficult. It is in most of the organs, but it's very difficult to find. This is different from blood or lymphatic vessel system. So this is artery here. This is lymph vessel. These two are PVS. So they are reacting artery with fluorophore conjugated antibody against CD31. That's a blood vessel biomarker. And LYV1 is lymphatic vessel biomarker. You can see this one is reacting, this one does not react. So it is different from blood or lymphatic vessel. If you look at this vessel very in detail, this one was damaged, but it should be like this. You have these subvessels inside, and this is SEM. You can see this little thing, small things inside, and then this is the PV. This is a confocal microscope of PV. And one of the distinct features of this PV is its nuclei is like a rod shape. It's not round. And if you look at the cross section here, you see there's a lot of little holes. That's a sub-PV. So just to summarize the unique feature of this one, you have this here, outside one has a hole larger than usual dye molecule. So when you apply dye around the place that PV is in, it absorbs the dye preferentially, which means blood vessels are not stained or lymphatic vessels are not stained, but this holds the dye. So that's one feature. Another feature is that this nuclei, they are elongated, not the circular. And then also multiple vessels are inside of the one vessel. So this is one which was harvested in the brain. So you have this vessel here, and then this is a node. And this is enlarged or magnified node here. And they did stain with DAPI. That's for nuclei. You can see this very, very, very small cells filled inside of the node here. So when they isolate this cell, which is very, very difficult to start with, and they react with the antibody against biomarker, that's actually expressing stem cell biomarker OCT4, Nano, and CD130. So this one has some kind of property of a stem cell, but we don't know. We haven't studied a lot yet because it has been so difficult to harvest. So various PVS that they found, it's in the intestine here, I mean on the surface of the intestine, small intestine. This is within, inside of the blood vessel. So this one is PVS, this is blood vessel. This one is very difficult to do because you have to remove all the red blood cell because it's really strongly absorbing light. This one is on the surface inside of the endocardium. And then they find that it is usually high, at the present high density in the adipose tissue. This one is brain. And this one is spinal canal. It starts from the brain and it goes through the spinal canal. So I think there's some kind of communication problem. I mean the network from here to. If you can use this one to do drug delivery, you don't have to worry about blood-brain barrier. This one is inside of the lymphatic vessel. There's a node here. It's branching out here. I'm going to show you a couple of movies. This is lymphatic vessel here. This little thing here is PVS, and this is a node. And as you can see, without staining, it's very, very difficult to see. So it's a live animal. All the film that I'm showing is live animal. You can see this PVS is floating inside of the lymphatic vessel, right? So what they do is, because it's so difficult to see, they fill the lymph vessels with the Asian blue, which is blue. You inject it, so it'll go all the way here, and you wait, and the lymph fluid is gonna clear out everything else except PVS because it has a hole, so you can take the. This one is done that way, and you have this forceps here. They are pulling out this PVS out of the lymphatic vessel. Lymph vessel does not get stained, so it's still clear. Is they pulling out the vessel? I'm going to go back. So it's highly elastic, so once it is cut, it rolls up like that, and you have forceps and you have a little dot here. And we try to do like a proteomics to get biomarkers. I don't know how to wash things because this is all rolled up, and then it's just so difficult. So in the brain, they find another one around here, and it's transparent here, as you can see. This is what it is here. So unless you have experience on harvesting this one for a long time, it is just simply too difficult. So, and some of the things that I just talked about, they inject dye through the lymph nodes, and if you see here, you have this thing, lymphatic vessel, you see this thing here, all these. Another one, it's from here to here. You have this lymphatic vessel, and then inside the lymphatic vessel, you have this PVS all the way. Another one, it's actually branching out somewhere and then joining together like this. Again, you see some of this branching. Okay. So far, I've seen the literature about 17 different organs from 7 different animals. And then most of the times they were able to find PVS in the organs. The very, very interesting thing then, what I am interested currently is because I need to tie this one to some kind of disease. Do you know what the xenograft is in the cancer model? What it is, it's not actually like a breast cancer. It's breast cancer put into the mouse somewhere. It's not actually human being having breast cancer. It's different. So we do xenograft all the time. That's the only thing you can do. You cannot actually make the breast cancer model very well. It's very difficult. So they were doing xenograft in the mouse, you probably use a nude mouse, placing the cells and then let it grow, so you have this tumor growing. And then we found that when the xenograft or this cancer tumor is growing, we see this PVS much more at a higher density. It's we did about, not we, but like the people did about 6 different xenografts, and this is the only one that we did. And all of them, they found that it is much more densely populated in the cancer. So the next study that they did was, it's not what I did, so Dr. So's group did. So they electroporated quantum dot in the cancer cell. You know what electroporate is? So what it is, basically you put a mild electric field, then the cell membrane gets loose, the particle gets in there. So when it is dividing, it's still, but the cells are still alive, it still contains the quantum dot, so it gets shiny. So they did the xenograft again. This is a primary cancer site, and the secondary one, secondary another one. And this is the fluorescent microscope. You see these cells here. One is, this is lymphatic vessel, and this is PVS. You can see a lot of cells are shown in here, very at a high intensity. So when you compare the intensity between the lymphatic vessel and then PVS, you have a much higher intensity coming on. This one is not standard, you cannot see well, but there are PVS here, and then the quantum dots are actually located in the node at a higher density. Here, this is ovarian cancer, and this is lung cancer. So another person put, do you know what green fluorescence is? Protein? It expressed the fluorescence. So in the nude mouse, they put the green fluorescence tumor. So it's growing. So you see this shining thing here. It's a primary cancer, secondary. Between two, you have this PVS. When they looked at this one, there are cells moving. I don't know if it's moving this way or this way, but it is moving here. You can see this one. Second example, another one, primary cancer and secondary. You can see this thing moving here. Another person did green fluorescence animal regular xenograft. So whatever is growing in the cancer, if it is green, then they think it's from the host. When they see this one, they have this green thing in the tumor. So another person did, this one. What they did was, they did use the lymphoma, and they analyzed the cell in the PVS in the tumor, and what kind of cells are inside. This is human origin. So which means that's from the tumor. At the same time, when they analyze the cell type, it is expressing some type of stem cell. So what they're thinking is, this is holding the cancer stem cell, probably. It's not confirmed, but they did the first study. So far I haven't said anything about meridian because as soon as I talk about acupuncture, people think it's very non-scientific. But the initial researcher, he studied this one because he found that one subtype of PVS is inside of the skin. That particular one is responsible for acupuncture therapy. He actually located all those. If I start with this, like, oh, she's talking about nonsense, and that I'm putting this one at the last one. Some of them are. So what the first researcher did a lot of work, but we have to confirm all this, whatever he's done, again, because he suddenly disappeared in the data from North Korea. Most of the study that we did, it turned out to be true, but we were not able to do all, but some of them are actually coinciding with this one. They did this one here, which is this, and they did this one. It's at the center. So they coincide with the meridian. And my question to you is, I think the first thing that we have to do is knowing the biomarker of PBS. And now we have a problem about getting enough sample and the clean sample. How do we do? This is micro size, or less than micro size. MEMS group, or we call NEMS group. Is there any way we can actually, we also try to put the nanoparticle to image it better. It's very, very difficult to put any, it's a live animal, it's moving, putting this one, and then if there's any air gap, nothing goes through. So, what do we do about this microfluidics to do study PBS? How to harvest, how to inject anything. Because if I can inject this one through this one, I can map it little bit by little bit. We just cannot do. The best thing that we can do is we pull the glass and put the nanoparticle and inject. Probably 1 out of 10 times it might work. There has been something that they worked okay, but it's not consistent because it's so difficult to do. And the microfluidic, microsize is a completely different story. So the question is there anything that you have an idea on how to study on that? The second thing is, do you think it's believable? And I believed, and I went to seminar, to give a seminar in this particular lab, and I said, forget about what I'm talking about, let's listen to whatever it is. I think it's scientifically confirmed, but I do not know whether you guys believe it or not, because we've been having a lot of problem about being reviewed well, and then a lot of people, well, how come we didn't find it yet? So that's the status, and this is my idea about PBS is I think locally repairing damages as well as communicating throughout the body. I think it's a very, very important organ. So now you're the third audience in Spain who knows about this one, and you can certainly talk about it. I'd be happy to leave any articles that I have copy. So, if you give me USB, then I'll be happy to do that. But before then, I'd like to get your opinion about this system, and if there's anything you can help me on PBS harvesting or injecting things. MEMS group.
Okay, so let's thank the speaker and we can continue the discussion in the coffee break.